Alrighty, now we are on to deactivating groups. What exactly is a deactivating group? Well, it's the opposite of an activating group. As an activating group is going to be electron donors, deactivating groups are going to be withdrawing groups. And by extension, that means they're going to remove energy from those aromatic pi electrons. We often remember how in activating we said they were ortho-para directors. In this case, it's going to be the opposite. It's going to be meta-directing. That means we're going to get it roughly about 90% meta and 10% ortho and para. Alrighty, so we have NO2 here. We know that this is a withdrawing group, but why is that so on an aromatic ring? Why is it pulling electron density out? Well, here's why. So if we draw the resonance structures here, I first want to draw this one where we take these pi electrons and we make a double bond and push electrons onto this oxygen. Looks as such. Alrighty, we get that, and we get a double bonded N. O minus, and then O minus. So we can see that it's going to pull electron density by resonance, because then these pi electrons will go here. Oops, like this. Notice how the meta, and this isn't important to know, notice how the meta positions do not feel any positive charge. It's only the ortho and para, kind of opposite of what we've seen so far. So we have that one, and then these pi electrons go like that. Oop, did not mean to draw that. It goes like this, yes, very nice, muy bueno. And NO, and then O, minus, minus. Okay. All right, so these are our resonance structures, and if we draw the hybrid here, kind of like we did last episode, we have our aromatic ring. I cannot draw these cyclohexane rings. If there's one thing you should know about me, it's that. And then we're going to draw just NO2 here, and we'll draw the conjugation of those electrons. So if we look at this, we know it's electron withdrawing because of the positive charges it induces on the ring, and because it adds it's pulling electron density with these electronegative oxygens on the ends of that nitrogen, and it makes this partially positive in both of the ortho positions and the para positions. And this lowers the reactivity for an electrophile. Remember, an electrophile is electron poor. Positive does not attract positive. No, this is like, I don't even know what reference to make. This is like pineapple on pizza. It just does not happen. It repels me, right? Repulses me even. And this just doesn't happen. Instead, an electrophile would much rather go to a place where there is some electron density, which would be right here or right here. And we know that it's 1, 2. And specifically, ortho-meta-para, that only really involves benzene rings. And in this case, it will only go to the meta position. So meta only. Alrighty, so I want to do kind of what we did with activating groups, where we showed a hypothetical ortho-meta-para attack, and I want to do it here with nitrobenzene, just to show you the differences in stability. So we're going to do a halogenation like activating groups. We're going to add our bromine gas, and then use our catalyst here, iron tribromide. Right, and we're going to do a hypothetical ortho attack, right? So if we do that, we're going to get this molecule here. And we're only going up to the sigma complex in the mechanism because that's important. So we're going to do NO2 to actually show the sigma complex and its resonance forms. So we have oops, I forgot to actually add my NO2 group. That would be really helpful, wouldn't it? Or my bromine group, I should say. So we have this here. Sorry about that. We have our bromine and our NO2 group. And we see a positive charge on the NO2 group. Now this is very, very, very important, so pay attention. You're gonna look at this and you're gonna say, okay, is this a primary, secondary, tertiary, quaternary carbocation? Well, we know that this is a tertiary carbocation, but what is it actually connected to? We know alkyl groups are electron donating. They allow hyperconjugation of those electrons. So two of the things it's branched to make it quaternary or tertiary is good because they're electron donating. But this thing is an extreme electron withdrawing group. Extreme. A nitrogen and then two oxygens that just hog electrons like pigs, right? So even though it's tertiary here, this withdrawing group is going to pull electron density away, right? So see the dipole arrow here. This dipole arrow, I'll draw the butt end again and make it all cool looking. That dipole is going like that. So that positive charge, even though it's in a tertiary carbocation, because it's getting electron density withdrawn from it from that withdrawing group, it's kind of deceptive. It's very unstable. All right, so let's now draw our other structures here. So these pi electrons will come up like this, and we'll see this here. We'll see a positive charge here, and it's going to be mostly unimportant stuff that won't really matter. Okay, and then come around this way, and we're going to get our final structure, which looks something like this. And then bromine, and then a positive charge. Okay, so we're going to do our summaries, kind of like we did already. So we have what are they called? Secondary carbocations. Jeez Louise. Okay, I can get the names right. But here we have a tertiary carbocation, but I'm going to add a little something special. And this fun color I don't think I've ever used on the channel before. Bad. It's a bad tertiary carbocation, and we do not like that. Okay, and I'm going to show you why, right? Because of that withdrawing effect, we're going to see why just having our secondary carbocations is a lot better. So let's now draw, and we're going to save the best for last, the meta. Let me just make sure my webcam isn't blocking. That should be good. Okay, so if we do a meta attack, so we draw our NO2 group here, and we put bromine here. Let's say we do that there, and then these electrons. So we added a bromine in the meta position. What's going to happen to the sigma complex? Well, we get this structure. I'll draw this one. I'm getting kind of tired of the red. It's kind of an eyesore. We get this carbocation of the sigma complex. Pretty okay. I mean, it's secondary. So, and then let's draw our last structure where these arrows push this way. And I'll draw this one in orange because orange is a very underrated color. Not a lot of people like orange. Orange is very fun though. We love orange. And bromine, and then we'll just draw our positive charge right here. I mean, we kind of have to, right? So let's count them up. Let's see. Secondary, secondary, secondary. So secondary, secondary, secondary. Pretty okay. I mean, compared to if you were to compare our ortho from up here, our ortho to our meta, we have a really bad carbocation resonance structure in our first resonance structure that we draw, right? That is a terrible carbocation, and when you compare the two, meta is a more stable sigma complex, and therefore will be selected for. And just to dot all our I's and cross all our T's, we're going to draw the final, what's it called? The para position, just to show you that this one's bad too, in case you didn't believe me. We're going to go with brown. Everyone hates brown. I hate brown too. Trust me. Brown is a stinky color. It's poop color. No bueno. Okay, so we're going to add our bromine here. We'll say we had a pi bond here that we broke, and then, oh god, this is a big eyesore. I regret doing this. Green. We love green. We've done green. Have we done green yet? Yeah, we did it for a bracket, but can't go wrong with green. Okay, so we're going to see from our sigma complex, we're again going to get that terrible, disgusting, tertiary bad carbocation, like this, right? So that electron withdrawing group is right there, stealing electron density from that already electron poor carbon. It's like, why are you doing this to me? It's literally like fucking torture. I mean, come on. And then our final one here is this. So, and then I'm getting a brain fart. This sucks. Like this, yes. Okay. I do have a brain after all, guys. Bromine, that one, and that way, and then our NO2, and we have our positive charge here. So yeah, let's compare once more. We have secondary, secondary, bad, tertiary. So that one and bad. So remember, when you look at the differences in distributions of your products, remember you're going to get meta the most because it doesn't have that bad tertiary carbocation that we spoke of. The others, you'll get about anywhere from like 8 to 10% on average. Hypothetical number, but still you'll probably get around that for your ortho and your para combined. Okay, that was deactivating groups. Remember, activating are ortho para directors, but deactivating groups are meta directors. I hope you guys enjoyed this video. Make sure to check out my next video where we talk about halogens. And they may seem like deactivating groups, but we'll see why they're not. So make sure to tune into that episode. Have a wonderful day, guys.